this video, we're going to be dealing with a column that is filled with liquid, and there is a height difference in this column. So there's position 1 and position 2, and so within this column there's going to be no pressure difference. And so there is going to be a balance of forces though. So this is going to be because the weight of the fluid in the column will be counterbalanced with the shear stress force. So what we want to do in this video is establish the fact that the fanning frictional factor for laminar flow is equal to 16 over Reynolds number. And so to do that, we're going to begin by starting with this vertical column and balancing the forces. And so the weight of the fluid in the column is going to be the density of the fluid times the volume of the fluid, so that's going to be pi r squared times the change in the height times the gravitational acceleration. And so that's going to sum to 0 with the shear stress times the area, so that's going to be 2 pi times the radius times the change in the height. And so if we cancel out like terms, we're going to cancel out the pi, one of the radius is going to cancel out, the change in height is going to cancel out, and so we're going to be left with the density times the gravitational acceleration times the radius plus the shear stress times 2 is equal to 0. So if we isolate the shear stress, that's going to give us negative density times the gravitational acceleration times the radius divided by 2. We also know that shear stress is defined as the viscosity times the change in velocity with respect to radius. And so if we take these two and set them equal to one another, that's going to give us the viscosity times the change in volume with respect to the radius is equal to negative density times gravitational acceleration times the radius divided by 2. And so we can move the viscosity over to the right side, and so that would give us this differential that we can separate and get the integral of it. So if we have the change in volume is equal to the negative of the density times the gravitational acceleration times the radius divided by 2 times the viscosity dr, we can get the integral. And so that's going to give us the velocity is equal to negative times the density times the gravitational acceleration divided by 2 times the viscosity times the radius squared over 2 plus a constant of integration. And so we know that as the velocity approaches 0, the radius is going to approach the outer radius, which we can define as big R here. So that's going to give us the 0 equals negative density times gravitational acceleration over 2 times the viscosity is equal to capital R, the outer radius squared divided by 2, plus the constant of integration. So then we can isolate the constant of integration, so that's going to give us constant of integration is equal to the density times the gravitational acceleration times the outer radius squared divided by 4 times the viscosity. So we can plug that in to this equation up here, and because this is a negative and this is a positive, we'll switch them around. So we'll have the velocity is equal to the density times the gravitational acceleration times the outer radius squared divided by 4 times the viscosity. And so if you were to simplify this, you can get the velocity equals the density times the gravitational acceleration divided by 4 times the viscosity times the quantity of the outer radius squared minus the radius squared. And so relating the velocity to the flow rate, we know that the flow rate can be defined as velocity times the area. And so here it's going to be a change in area, so the flow rate is going to be the integral from 0 to the outer radius of the velocity times the change in area, because as we change position, you're going to change the area. And so if we plug in our velocity derived equation here into this equation, and we know that area is going to be 2 pi times the radius. So plugging this in for area and plugging this in for the velocity, we're going to have the flow rate is equal to the density times the gravitational acceleration divided by 4 times the viscosity times the quantity of the outer radius squared minus the radius squared times 2 times pi times the radius. So this is all going to be the integral from 0 to the outer radius with respect to radius. And so if we factor out constants, that's going to give us 2 pi times the density times the gravitational acceleration divided by 4 times the viscosity. We will distribute this r into this quantity here, so that's going to give us integral from 0 to the outer radius of the outer radius squared times the radius minus the radius cubed with respect to the radius. So solving that integral, it's going to give us 2 times pi times the density times the gravitational acceleration divided by 4 times the viscosity times the quantity of the outer radius squared times the radius squared divided by 2 minus the radius to the 4th power divided by 4, this evaluated from 0 to the outer radius. So that's going to give us 2 times pi times the density times the gravitational acceleration divided by 4 times the viscosity times the outer radius squared, plugging in the radius, that's going to give us the outer radius squared again. Combining these two, it's going to give us the outer radius to the 4th divided by 2 minus the outer radius to the 4th divided by 4. If we plug 0 in, that's just going to give us 0. So basically this is 1/2 minus 1/4. So it's going to give us 2 pi times the density times the gravitational acceleration divided by 4 times the viscosity. 1/2 minus 1/4 is 1/4. So that's going to give us r outer radius to the 4th over 4, which we can simplify. So crossing out, that's 4 and that 2. This is going to give us with a 2 remaining in the denominator. So again, simplifying further, we're going to have pi times the density times the gravitational acceleration times the outer radius to the 4th divided by 8 times the viscosity. So that gives us the flow rate. And so now to relate to laminar's frictional heating, we can use Bernoulli's equation, which is the pressure at position 2 minus pressure at position 1 divided by the density plus the velocity at position 2 squared minus the velocity at position 1 squared divided by 2 plus the gravitational acceleration times the height at position 2 minus the height at position 1, which is just the difference in height, equals the frictional heating. And so if we know that there's no pressure difference, so this is equal to 0, and the area, so the volume is the same, so that's going to equal to 0 as well. So we're left with the gravitational acceleration times the change in the height is equal to the frictional heating. And so how can we relate the flow rate to this part of Bernoulli's equation? Well, we know that there is a gravitational acceleration here and a gravitational acceleration here. So if we were to isolate the flow rate and isolate the gravitational acceleration, we would be left with 8 times the flow rate is equal to pi times the density times the gravitational acceleration times the outer radius to the fourth divided by 8 times the viscosity. So now if we were to isolate the gravitational acceleration, we would have the 8, any of these markers work, we would have 8 times the viscosity times the flow rate divided by pi times the density times the gravitational acceleration, times the radius, outer radius to the fourth is equal to the gravitational acceleration. So if we plug this in for this gravitational acceleration here, we get that the frictional heating is equal to the 8 times the viscosity times the flow rate times the change in height divided by pi times the density times the outer radius to the fourth. Frictional heating can also be written and defined as 4 times f, lowercase f, times the change in the length divided by the diameter times the velocity squared divided by 2. So this lowercase f here is Fanning's frictional factor. And so if we were to set these two equal to one another, we have 128 times the viscosity times the flow rate times the length. So because we're going to be simplifying, this length here is also change in the position. This was earlier the change in the height here, which we defined as length because it was negative, which is really just it's the length of the cylindrical column. And so just for simplifying purposes, we can put that as the change in x because that's the same thing, divided by pi times the density times the diameter to the fourth is equal to 4 times the frictional factor times the change in length divided by, or the change in position divided by the diameter times the velocity squared divided by 2. So what we can do is simplify this because the 4 and the 2 are going to simplify for this to equal 2, and then if you divide both sides by 2, this is going to equal 64. And then the change in position is going to simplify and cancel out. So then if you were to move the velocity squared over the diameter, well, this diameter is going to simplify with this diameter, leaving a diameter cubed. And then if you move the velocity squared over to the other side, you would get that the friction factor is equal to 64 times the viscosity times the flow rate divided by pi times the density times the diameter cubed times the velocity squared. And so the flow rate is equal to the velocity times the area. And so the area, the velocity times the area is changing with respect to radius. So that's going to be 2 pi, which are the constants, and then the integral of the radius dr. So that's going to equal to velocity times 2 pi times r squared over r. And so, r squared over 2, the 2's will cancel out. So that leaves us with the velocity of pi times the radius squared, but the radius is defined as the diameter over 2. So squared, that's going to be the diameter squared over 4. And so that can be plugged in for the radius here. And so plugging that flow rate in for this flow rate, that's going to give us 64 times the viscosity times the flow rate here, which is velocity times pi times the diameter squared divided by pi times the density times the diameter cubed times the velocity squared times 4. And so the diameter squared is going to cancel out, leaving a diameter in the numerator. The velocity and the velocity squared is going to cancel out, leaving just a velocity in the denominator. The pi's will cancel out. The 4 will cancel out the 64, leaving a 16. And so what we are left with is 16 times the viscosity divided by the density times the diameter times the velocity. And so Reynolds number is defined as the density times the diameter times the velocity divided by viscosity. And so because this is just the reciprocal of that, that means the Reynolds number is going to be in the denominator. So that shows us that Fanning's frictional factor is equal to 16 over Reynolds number.